What specific problem does PLANSEARCH aim to solve within the context of code generation for large language models?
PLANSEARCH aims to address the problem of low diversity in the outputs generated by large language models, LLMs, during code generation, which hampers the effectiveness of search methods at inference time. The lack of diversity often results in repeated and similar code outputs, particularly when using methods like greedy decoding, leading to minimal performance gains from additional compute. By focusing on searching over high-level plans or ideas rather than individual tokens or lines of code, PLANSEARCH encourages exploration of a broader conceptual space, thereby increasing the variety of generated solutions. This approach has been empirically shown to outperform standard sampling methods, as it allows for the generation of more diverse and potentially correct code solutions, ultimately improving pass rates on benchmarks like LiveCodeBench. Thus, PLANSEARCH seeks to enhance the overall performance of LLMs in code generation by maximizing the exploration of ideas and sketches before arriving at the final code implementation.
How does the PLANSEARCH method work? Illustrate step by step the core components and processes involved in PLANSEARCH.
The PLANSEARCH method operates by systematically exploring the idea space to enhance code generation through a series of structured steps. First, it begins with the problem statement, P, and prompts a language model to generate initial observations or hints about the problem, denoted as O*1_i. Next, it creates all possible subsets of these first-order observations to form candidate plans, which are combinations of observations that may help solve the problem. This process is repeated to generate second-order observations, O²_i, from the first-order subsets, effectively building a tree of observations that can be explored for diverse ideas. Once the observations are generated, PLANSEARCH prompts the model to derive natural language solutions based on these observations, which are then translated into pseudocode and finally into executable code. This method emphasizes the exploration of diverse ideas by allowing the model to generate multiple candidate plans before arriving at a final solution, thereby increasing the likelihood of producing correct and varied code outputs. The overall goal of PLANSEARCH is to maximize the exploration of ideas, leading to improved performance in code generation tasks.
Can you provide a simple example of how PLANSEARCH generates a plan before producing code? Walk through the main steps with an illustrative problem.
PLANSEARCH generates a plan before producing code by following a structured approach that emphasizes the exploration of ideas. For instance, consider a problem where the task is to implement a function that calculates the factorial of a number. First, PLANSEARCH prompts the model to generate initial observations about the problem, such as factorial of n is n multiplied by factorial of n1, and base case is when n equals 0. These observations are then combined into candidate plans, which may include various ways to express the recursive relationship or iterative approach to solving the problem. Next, the model generates multiple candidate plans by exploring different combinations of these observations, ensuring a diverse set of ideas. Finally, each plan is translated into pseudocode, which is then converted into the final Python code solution. This method allows for a more thorough exploration of potential solutions, increasing the likelihood of generating correct and diverse code outputs.
What are the practical advantages of using PLANSEARCH over traditional methods like repeated sampling, especially in terms of performance metrics and output diversity?
PLANSEARCH offers significant practical advantages over traditional methods like repeated sampling, particularly in enhancing performance metrics and output diversity. Specifically, PLANSEARCH achieves a state-of-the-art pass-at 200 score of 77.0% on LiveCodeBench, which is a substantial improvement over the best score from repeated sampling, pass-at 1 equals 41.4% and pass-at 200 equals 60.6%. This method effectively increases the diversity of generated code outputs by searching over high-level plans rather than individual tokens or lines of code, which leads to a more efficient exploration of ideas. The empirical results indicate that the diversity of output code is highly correlated with performance gains, suggesting that the exploration of plans in idea space is crucial for improving code generation. Furthermore, PLANSEARCH outperforms both standard repeated sampling and the IDEASEARCH method, demonstrating its superior capability in utilizing inference time compute to generate a wider variety of correct solutions.
How did the authors validate the effectiveness of PLANSEARCH, and what datasets or benchmarks were utilized for testing its performance?
The authors validated the effectiveness of PLANSEARCH by conducting experiments on 3 coding benchmarks: Live Code Bench, Human Eval Plus, and MBPP Plus. They demonstrated that PLANSEARCH outperformed both standard repeated sampling and the IDEASEARCH method, achieving a state-of-the-art PASET 200 score of 77.0% on Live Code Bench, compared to a PASET 1 score of 41.4% without search. Additionally, they provided empirical evidence that searching over plans in idea space significantly increased the diversity of generated code outputs, which correlated with performance gains. The experiments included generating observations and sketches, followed by translating these into code, thereby showcasing the method's ability to enhance code generation through effective exploration of ideas. Overall, the results indicated that PLANSEARCH not only improved pass rates, but also effectively utilized inference time compute to generate diverse and accurate code solutions.
What were the main results achieved with PLANSEARCH in comparison to other methods, and what implications do these results have for future research in code generation?
The main results achieved with PLANSEARCH indicate a significant improvement in code generation performance compared to other methods, specifically outperforming both standard repeated sampling and the IDEASEARCH method. For instance, applying PLANSEARCH on Claude 3.5 Sonnet achieved a state-of-the-art PASET 200 score of 77.0% on Live Code Bench, which is a notable increase from the best score without search, PASET 1 equals 41.4%, and the best of N sampling score, PASET 200 equals 66%. These results suggest that searching over plans in the idea space enhances the diversity of generated code outputs, leading to more effective use of compute at inference time. The findings imply that future research in code generation should focus on improving the diversity of model outputs through enhanced search strategies, potentially reimagining post-training objectives to prioritize exploration of diverse ideas rather than optimizing for a single correct response. This could lead to more robust models capable of generating high-quality code solutions across various benchmarks.